Hello, guys. In the last class, we studied some tests of, not really tests, but some features of the random number generators. And we found out that there are three aspects of random number generators that are important: uniformity, periodicity, dimensionality. So these are three of the features of random number generators that we have to care about. And fortunately, there are some tests that we can use for probing these features and test if the random number generator is good enough for our application. But before going to the tests of random number generators, let's see some concrete examples of applications of Monte Carlo method by electronic devices, electronic computer, and just to get some feeling about applications and how important the random number generators are. So we are going to see some simple applications. The most simple application is sorting some number of events according to a given distribution, let's say this one. And this is something that at this point of the course you already tried, and if you did all the activities proposed, you certainly prepared already a code for sorting events according to a distribution given by some simple function of one variable like this one. Okay. So this is something that you already did. So let's see something a little bit more complex. Let's say that your probability distribution is a sum of two functions. And the functions can be anyone, and even very simple ones like this. So the activity that I propose to you now is to sample a number of events following this distribution that is given by a sum of two functions like this one. And so you have to write a code. You probably wrote a code for sampling distributions according to one of these functions, and or something similar. So you can use it to sample the distributions for the two functions. And there are different methods to do it. Some more than one will work well, but some that seems to be intuitively correct, they are not. So I would like you to test different methods for sampling this distribution that is given by a sum of two simple functions. Okay, so you have to do it and plot in the same figure the histogram of the sorted events and the value of the function of the distribution. So you can compare what you get from the Monte Carlo method with the expected distribution. Okay, so making plots is a very good way to check if your Monte Carlo method is working properly or not. Well, there is another kind of problem that is a little bit different, that is sorting points in a space or vectors in a space with more than one dimension. So this is a little bit more complex than what we did before, because to get one point in the space with a dimension d, you need d components, so you need to sort d times a random number. So you needed d different random numbers to get just one point. So let's suppose you have a simple form, a cube or a hypercube in a d-dimension space, and you wanted to select components with random numbers between minus L and plus L, where L is the size of the edge of this region or this hypercube. And then you need to generate random numbers that are points that have the d coordinates of the points. And if they are randomly distributed in the space, you need one random number for each of the coordinates sorted in this interval. Okay, so usually your programming language will give a series of random numbers between 0 and 1. So you have to find out how to transform a random number between 0 and 1 to random numbers between minus L and plus L. Okay? Then you have all the coordinates. So every time you select, you sort a point, you need the random numbers sorted. Okay, so this is a little bit more complex problem, and as we saw in the last class, the main problem here, the main challenges for your random number generators are the periodicity, because you need a lot more random numbers for this problem, and the dimensionality, because sometimes random numbers may appear random in a series of numbers, but when you build points in a d-dimensional space, they are not really random, as we saw in the last class. So this is another challenge for the random number generators. So write a code. This is a second activity for this class. Write a code to generate a uniform distribution in a 1x1 square like this one. So you have the coordinates x and y in the space. You can imagine this is a surface. And you want to sort random numbers inside this square. This is very simple. You just need to sort R1 and R2, X and Y, and they are already between 0 and 1. So you get a random number distribution of a random distribution of points, and you can plot it. So it's a good idea to plot this and check if the uniform looks like uniform. Just look at it, you can find if there is any distortion. So let's see, a more interesting application is the use of Monte Carlo method to calculate the number pi to some with some precision that we can choose. So imagine that you have a circle inscribed in a square of with edge L, like this one. So you have the circle inscribed in a square. The area of the square, AS, is L squared, right? And the area of this circle is AC equal to pi times R squared. But R squared is L over 2 if the circle touch the edges of the square. So AC will be pi times L squared over 4 divided by 4. So observe that the ratio AC divided by AS is pi over 4. So this is a way to obtain the number pi. We just need to calculate the ratio between these two areas and multiply by 4. Now, notice that if you sort a series of points inside this square, some of the points will fall inside the circle, but some will fall outside the circle. Okay, if you have n number of sorted points, let's say nc is the number of points that falls inside the circle. Now, this is the first step of your activity. Using the concepts of statistical sampling theory, show that the probability to get the point inside the circle is PC of point X inside the circle is the number of points inside the circle divided by n. This is just the basic concept of frequency in probability theory. So you have to show that this ratio is equal to the ratio between the area of the circle and the area of the square. And this, as we saw, is pi divided by 4. So to do this, you have to use the concepts of statistical sampling that we saw in the second class. So this is one activity for you. And the second step in this activity is using your code that you wrote already to obtain a uniform distribution of points inside a square that you just did in the first activity. Obtain the value of pi up to 10 to minus 5. This is the precision we want to achieve. So you can think about how many numbers you need, how many points you need to sort inside the square to get the number pi with this precision, and compare with the known value of pi that you can get in your electronic calculator. This third step is the following. Do the same as in item 2, but we now use a generator, the generator that you built some classes ago. You build this code following the von Neumann method. Okay, so you wrote a code to generate numbers using the middle square method developed by von Neumann. We saw this is not a very good method, but try to use it to calculate pi using the same procedure that you used here, using the random number generator of your programming language, and compare with the result that you get. Check what is more precise, which one will give a good result. And this is the activity, the second activity. So let's see now another application that's not much different from the previous. That is numerical integration, using Monte Carlo for numerical integration. In fact, Monte Carlo is mostly, you can see any use of Monte Carlo as an integration in a sophisticated space, but it's sometimes, but it is usually an integration. So suppose that you have a function fx that is described here by this curve, defining some domain. It's a simple function of one variable, and you are asked to evaluate the integral of this function. So what you can do, based on the method that you use to evaluate the number pi, you can do the following. You just draw a rectangle around the function, like this. And it might be, there is a lot of arbitrariness in when you choose the rectangle, but it's usually a good practice in order to leave areas much different below the curve and above the curve. So try to get areas that are similar. And then you are asked to calculate this integral of the function. How can you do it using Monte Carlo? we just saw that for pi you use the ratio between areas to calculate the integral. So you can do something similar. So how can you obtain this? I have here a description in the notes, but I use this figure to tell you how to do it. You draw this rectangle, sort uniform distribution of points inside the rectangle. Some of them will be above the function, some the curve, and the others will be below. Okay, so let any b and in index b like this be the number of dots of points that you got below the function, and any the total number of sorted points. So show that the integral can be calculated by the ratio nb over n. So this is an estimate of the integral of the function. So you have to show it using this statistical sampling theory. It's more or less like you did for showing that you can calculate the number pi in the last method. So try it for a different function, sin of x, for x between 0 and pi, and compare it to the expected value. So you can get the expected value and compare it to the value that you obtain using Monte Carlo method. And then you can try it for different functions of your interest. You can always compare what you get by the Monte Carlo method and what you get analytically or by other means. Okay, so this is the class for today. You have a lot of activity, but it's important to do it because you get practice with Monte Carlo, and also you develop some codes that you need in the next classes. So this is the activity for this week. Read the notes and try to perform these activities. Okay. See you next week.